Well, hello again everybody. Now I was at work last week and I was crawling around in the back of our old stores and I came across this old test jig which I seem to remember I had to put this thing together to test some equipment we were designing at that time. Now I have to admit my memory of what we were actually doing is a little bit hazy because it's probably 10 or maybe even 15 years ago that we were doing this. But I seem to think we were working on a microprocessor system. And that microprocessor system was mains powered. And as part of the equipment's operation, it had a number of user settings, and it also had to remember maybe what it was currently doing at any time. And the problem was, of course, is that if you ever got a mains power failure, the microprocessor would lose power and it would lose all the contents of the RAM settings. Now this piece of equipment was only a piece of cheap equipment, and we couldn't afford to do things like put memory backup batteries in it, and we didn't have these super capacitors that they have today. So what we did was we built mains fail power detection into this piece of equipment. So when the mains actually failed, we would detect that, and then we would have a certain amount of time before all the capacitors discharged in the power supply. We'd have just about enough time to shift the contents of the RAM into an E-squared memory. And again, even early E-squared memory back in the day wasn't particularly reliable, and you didn't have a huge number of write cycles. Now it looked as though you did have a lot of write cycles, but when you actually got down into it, because of the way the memory was paged and all the rest of it, although it looked like you had tens of thousands of writes, in practice it probably worked out much less than that. And of course the worry was that if you had a bad power supply or even just brief mains interruptions, we were going to start writing to this E-squared memory and effectively wear it out. So what we needed was just a piece of test equipment where we could vary the power supply and cause some short power interruptions, so that we didn't have this thing constantly falsely triggering and moving the contents from RAM into E-squared, just doing it constantly under fault conditions or just because of noise on the mains. So this is a piece of equipment I seem to remember I knocked it together very quickly in about a morning just so we could do some testing. So better than waffling on for about an hour, it's probably easier just to give you a demonstration. So we've got a microprocessor here, and I think from memory it's something like a PIC. It could be a PIC, would it be an 844, something like that. Again, it's covered in dirt and dust. I can't even read it. Like I say, this thing is so old. And the microprocessor is just connected to a 7-segment display, or a couple of 7-segment displays. I think I already had the board from memory. It was one of them things that you have a box of bits and you basically just screw a few different parts together to get something working. So I seem to think I already had this PIC microprocessor board wired up to do something else, and I just repurposed it at that time. So we've got the PIC board here, and that PIC board has got a 5-volt regulator on it, a PIC. It's got some test lights, which I can't remember whether we use them or not. It's got a push button, and it's got a piezo buzzer sounder. And over here we've got 2 7-segment displays. Well, it's got more than that, but I seem to think, again, I only use the 2 displays on it. So what you can do is, these numbers here represent the number of mains cycles at the moment. So if I press the up button, it counts up. If I press the down button, it counts down. But what these represent is single mains cycles. So again, I'll give an example of how this works, and I'll probably just have to just blank the bulb out, because otherwise the camera will just wash out. So I'm going to turn the power on now. So we've turned the power on and the bulb's lit up. We've got a full 50 Hertz, 50 main cycles being supplied to the bulb. So this is the test button here. We press it and nothing happens because we're supplying 50 out of 50 main cycles. So what I can do is I just press the up button, and we've got that 1, that's gone to 1 now. So when I test the push button again, what it's going to do, it's going to take out 1 main cycle. So we're going to lose 1/50th of the power going to the lamp. So we'll just press that. and hopefully you can see on the camera that's flickering. So we'll just extend that. We're going to knock out now 10 main cycles, or 1/5 might be a better way to put it. So when I press the button now, the lamp will go out for a longer time. So I am holding the button down there, I'm not just dabbing it. So I'll hold the button down, hold it down again, and we can keep extending that. Let's do 25. So effectively what's going to happen now, it's going to turn the power off to the lamp for approximately half a second. And it also has another mode of operation which you can use. So if you turn the lamp off, and now I press the button, as it works the opposite way around. So I press the button now and it'll come on for half a second and then go off again. So what this allowed us to do is, it allowed us to actually just basically play with the software in this piece of equipment we were developing, and just making sure that it didn't falsely trigger. So if you lost one main cycle, it didn't care. But if you lost about half a second of main cycles, it would go into this routine where it basically backed up the RAM to E² memory. Now, of course, the other way we could have done the testing is basically just switch the power supply on and off. But there's no real way to actually do that systematically. You're never quite sure how long the power supply was turned on or off. So that's why I automated it. And also, to be honest, it just seemed like an interesting thing to do. So just to visualise whether the power was on and off, it was driving a lamp, but in parallel with the lamp was also a plug socket, and that's where we would plug in our device under test. Now, just to give a better demonstration of what's actually happening here, I've actually just got one of these little wall wart power supplies, but this one isn't a DC power supply, it's just a little tiny mains transformer. So this output's just AC. So we'll plug that in, and now we'll take you over to the oscilloscope. So this is the AC waveform coming in here, and you can see that I've been pressing the test buttons at various points. So if we just zoom in on that, we can see that when I press the test button at the 0 crossing point there, it took out one full cycle. So what I'll do is I'll just increase the number. Let's go for, I'm just going to set this for 2 now. So I'm hoping you can see there that we've taken out 2 complete main cycles. And as I increase the number on the counter, it just takes out more main cycles. Now, it's such a long time ago that I built this, I really couldn't remember in detail what was in this circuit. So I had to remove the cover and have a quick look of it. Now, before I get hundreds of comments, everybody saying what a rubbish circuit is, what I would say is I built this using parts that I had available under my workbench 15 years ago. There's lots of different ways that we could have built this. Many of them would have been much better and much safer. But I had to lash something up with and I only had a couple of hours to prepare, and this is what I came up with. So we actually turned the power on and off here using a TRIAC device, and that TRIAC is actually controlled through an opto-isolator. Well, again, I was actually using, I've just written it down here, something called an MOC 3021, and I had to again look up the data sheet for that because I couldn't remember what it was, but it appears that that is an optically isolated diac, and diacs are quite often used to trigger triacs. Now, the other part of the circuit we've got here is to do with detecting the mains crossover, which is, basically effectively the 0 volt point where the AC waveform, where it crosses over from either the negative or the positive part of the main cycle. Now, it's actually very, very common to actually switch a triac on at this 0 crossing point, and the reason that people want to do that is because there's no current flowing in the circuit. When the main cycle is at 0 volts, the potential difference is obviously 0 between your live and neutral. You don't really want to switch your triac on at the peak of the main cycle, because you'll be putting full load across it, and you'll be generating, you know, huge current spikes which will, you know, radiate. You'll not only risk damaging your triac by switching it on at the peak current, you'll also radiate a lot of EMI noise. So you don't want to do that. You want to switch the triac on and off at the zero crossing point. So what I did was I built a little circuit here to detect the zero crossing point. So what I do here is I've got a full wave bridge rectifier which is rated for the full mains voltage, and for mains voltage for here in my workshop, it's actually very high. It should be 230, but most of the time it's nearer to 250 volts. So the actual the peak voltage that we see across the output of the bridge rectifier is actually pretty damn high. So it could be anything up to 350 volts. Now obviously we can't connect something of 350 volts directly to the input of our microchip. There's a few different ways you can do zero crossing detection. I think this is probably one of the better ways to do it. The way that quite often it's done in domestic equipment, cheap and nasty electronics equipment, is literally they just connect the mains live connection to the input to the PIC via quite a high value resistor, I don't know, 20 or 30 megohm. And what they actually do is they use the ESD protection diodes in the front end of the PIC input to limit the current via this, to limit the voltage, to clamp the voltage. And the current is limited via a very high value resistor. But I don't really like doing it that way. I think having mains power anywhere near your PIC is not really a good way to do it. Now equally, this is not a great idea either, because I'm dissipating a huge amount of power in this 22k resistor. But yeah, this is what I did on the day. So we're outputting here, you know, approximately 350 volts when we're at the peak of the peak of the main cycle. We clamp that to 3 volts, 3.3 volts with a Zener. So even when there is 350 volts at the top of here, the voltage at this point here will only be 3.3 volts because I'm clamping it with a Zener. And then we take that again via another little current limiting resistor there, and we put this into the input of an opto-isolator. So what we actually get is we get pulses of we get a pulsed output every time the mains crosses the 0 point. So this will stay conducting. This opto-isolator will actually be switched on most of the time, but as the voltage just falls to 0 at that point there, as it crosses over, there'll be no power across that diode, no voltage across it, so that'll briefly switch off. And then I do some buffering here with a couple of SMIT triggers. Now I didn't actually need the SMIT triggers at all. I think I probably didn't know at the time when I built this is that the microchip PIC itself has some SMIT triggering on its inputs. But what I would say about the SMIT triggering on PIC inputs is they're pretty bloody awful. There's an awful lot of variance between one PIC and another. So often if you're using these PIC micros, it is often better that if it is something that requires SMIT triggering, it does have its use to use a proper external SMIT trigger. And I'm using a 74F14 here to do that. Now I did put this mains cover over it because under here there's a lot of mains components, mains power components, and yeah, there's lots of things here that are live to the touch, so I thought it was a good idea to put a plastic cover on it. Yep, so there's our Zener diode there, which is doing our clamping to the 3.3 volts. This is our opto-isolator here, which is basically just being switched on and off every time the main cycle passes its 0 crossing point. And then these are actually the mains control switching components. So the 8-pin device here in the socket, that's our diac, which is controlling the gate to the triac. That's that green wire there. It's controlling the gate going to our triac, and it's switching the mains power supply on and off. Now we've got a device down here. That's our SMIT trigger down there. And I seem to think that I've actually also got a couple of the gates on the SMIT trigger just buffering the output from the pick. Now I don't think I needed to do that. Again, I think the only reason I did it is because it was as easy to use up all 4 gates, because it's not a good idea to use gates floating in a device. Now I could have tied them down to ground, but I thought, well, I might as well just use them both. So I actually do buffer the output control lines from the pick that go to the DIAC to control the power. So the green wire here, that's our 0 crossing point. There's a brown wire. The brown wire is actually the mains drive. That's the thing that turns the power on and off, switches the DIAC on and off, and then turns the TRIAC on and off. And then the black and the red wire are just a 5-volt supply. Now earlier we had a look at the mains voltage on the digital storage scope there. Well, back in the day I didn't have a digital storage scope, so that when you saw that knocking out the waveforms on there, well, you saw it for the first time and I saw it for the first time. So it was quite nice to see that this piece of equipment was working as I envisaged it was. Well, you know what, I think we should have a closer look at some of the voltage levels and these various components. So let's have a go at that. So first of all, I think we should just start by using this really quite expensive Keysight oscilloscope. And I think we should start having a look at some of the mains supply. So I think what we will do is we'll just clip the ground connection of this scope probe, and we'll just clip that to the light. Yeah. Let's just stop. You probably thought that I wanted to talk about this wonderful circuit that I designed, or not so wonderful circuit for that matter. No. I don't particularly want to talk about this circuit at all, because this channel, it's all about the gear. So what we actually want to have a look at is some gear. Now, again, I know my audience, you know that it wouldn't be a very good idea to connect this scope probe to this live connection. Now, some of you might have spotted earlier that I was actually using an isolation transformer to power this piece of equipment up, but yeah, it would have been quite disastrous if we had actually connected this ground connection to this live terminal here. And in fact, it probably would have been equally disastrous whatever we'd have connected it to. So basically, if you want to look at mains powered equipment using an oscilloscope, if you want to look at the waveforms, yeah, this isn't the way to do it. Yeah, we don't want to use these kind of things. Back in the day, you might have used an isolation transformer, but unless you know what you're doing, you can very easily get into hot water. I suppose that the reality is, working with any type of mains powered equipment, you can get yourself in hot water very quickly. And I think unavoidably you're probably going to have to make your own mistakes and blow a few scopes up, which is what I did in the day, and hopefully you'll get a few rather nasty electric shocks and get thrown across the workshop, but they won't actually kill you, because I'm afraid that there's nothing quite like pain to actually reinforce learning. So we're certainly not going to probe around using a traditional oscilloscope and our grounded connection scope probe. Yeah, recipe for disaster, we don't want to do that. So actually what I wanted to show you today was this BWD 881 Power Scope 2. Now, well, that's a bit of a mouthful. Now, there's a few interesting things about this scope. I think one of the interesting things about it is that it was manufactured by a relatively small supplier of equipment and it comes all the way from Australia. Now, I think that this was made back in the day, somewhere in the late 80s, maybe the early 90s. Not exactly sure. Unfortunately, I haven't managed to find an operator's manual for this. I did manage to track down the service manual for it, but not the operator's manual. So what the heck is a power scope? Well, it's actually designed for working on, probably as the name suggests, is power systems. And the unusual thing about it, or what makes it a power scope, is that the inputs are differential pair inputs. So to explain that further, you'll find that these inputs aren't actually referenced to ground. So it actually gives you a positive and a minus there. So you could say that the -1 would be your ground connection, but it isn't ground. It's just your 0 volts connection. It has no reference to ground. And in fact, I can probably prove that. And I'm on the ground stud there, and there is no connection. Now, you did actually hear a bleep there, because the way that these wires are actually constructed, there is actually an outer conductor here. Now the outer conductor is grounded. In fact, I need to bring you in so you can see that. I keep wanting to call this a ground connection, but it's not a ground connection. If we look at the connector here, you actually see that there is an outer metal ring. Well, that outer metal ring is actually connected to ground, but the 0 volt connection, if you like, is the center pin. So it actually goes into the center pin of the connector there. So it's got what you might call, it's got a protective ground around it, but the actual connection to the internals of the scope is on the center pin, and that isn't grounded. So the other thing to prove is that this channel here, if we go on the 0 volts, it isn't connected in any way to the adjacent channels. So all the inputs to this scope are truly floating, and they are truly separated from each other. So yeah, so basically the inputs are differential, and that's very unusual. So I don't know what oscilloscope you've got on your bench at home, but I would be surprised if your oscilloscope at home goes up to 200 volts per division, which this one does. On the other hand, most scopes go to a lot less than 0.1 of a volt division, which is the minimum that this will do. But we have got a range of between 0.1 volt and 200 volts per division. And these are our probes. And I'll show you something else interesting about these probes as well. They are a little bit awkward, these things, but I'll show you anyway. We can actually take this apart, and they're actually really fiddly and annoying. So you can actually see that if we pull this scope probe apart, it's actually got a fuse in it there. It's actually got 100 milliamp fast blow fuse. So again, it kind of shows you that this piece of equipment is designed to be working on power systems, and you know, they want to make it as safe as possible. So they've actually gone for one of these, I don't know, is that about 1 inch wide, because they're trying to give you some electrical separation here so that you can't get arcing from one side of the fuse to the other. That's why, for example, they haven't used a little 20mm glass fuse. It's actually to give you this electrical separation. Now I'm going to have to try and reassemble this, and these are buggers to put back together, I promise you. I need that thing, I need the spring, I need this little safety cover. Got to get this board to go in this little groove here. Has that gone in? Hopefully it has. Where's the other bit? That goes into there. Where's the back cover gone now? Gotta get the back cover to go down. Come on. There's little slots in everything, so the circuit board has to line up. It's as though they've designed it to be as awkward as possible. Oh, and that, I can't get that to go in there, so I suspect what's happening is the... yeah, I'm going to get really annoyed again in a minute. I knew I shouldn't have pulled these apart. These are buggers. I know exactly what's going to have happened. This board will have slipped out of these... this little guide there. I'm assuming that it's designed this way to make it as kind of spark proof as possible, so if you do get some electrical arcing in here, they're trying to make sure that arc doesn't escape the enclosure. So there's lots of little caps and seals, but the upshot, if you're actually working on this scope, these scope probes, is they're just tremendously annoying to use. Right, we've got that back together, because even the probe tip here is it's got a little spring-loaded shroud on it. But interestingly enough, the shroud doesn't come to the very end, so it's kind of semi-pointless. I'm guessing the idea of that is if you've got it plugged into something, you haven't got the whole length of it exposed. In fact, I built up this little test plug the other day just so we could make this video. So we can see that, you know, in the UK the brown connection is live. So what we could actually do is we can plug that into there. And even if we slightly withdraw it, it's still, you can't get your fingers on the actual live part because it's got this sliding guard. And that's common for a lot of high voltage equipment. So the oscilloscope that you've probably got on your bench, it's probably got a nice little hook probe. Well, this is the equivalent of a hook probe on this scope. And yeah, so quite a big probe, which is, again, it's designed to keep you as far away as possible from the piece of equipment you're working on. It's just for your protection. But I'll just show you this probe in action. Hopefully you can see this probe. Look at that. Blah, 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 blah. Blah, 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 blah. Blah, 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 blah. So we've got our scope probes now. Internally, these are both exactly the same.